Okay, we're back again. Today we're going to be looking at the different ways that two lines can exist with one another. So we're going to first start with the classic example. So you see that there's three different situations that can happen. So the first situation, that's the most common, the one that you've been seeing the most often, is that two lines can intersect once, right? Because they're lines, they're not going to curve again and touch each other in a different location. So we call that one point of intersection. Okay, so that's option one. And what that looks like is what you've seen. So we have a line going this way, a line going, say, this way. It doesn't really matter. And right there, where they intersect, is the POI. So there's one point of intersection. Now, how can you tell that you have this situation? So lines intersect once. They have different slopes, right? Totally unrelated, different slopes. They can have the different or same y-intercepts. Because the point of intersection could be the y-intercept. That just could be where they touch, so that's why it would match. Most of the time, though, it is different. So different slopes, different y-intercepts most of the time. When the lines are in standard form, so this is useful in y equals mx plus b form, right? You can compare. How do the slopes and the y-intercepts compare to each other? But when in standard form, unrelated coefficients for x and y when in standard form. So you don't see any relationship happening between the two equations. They just look totally different from each other. So that's the common example that, again, you've seen us do now over and over again. Now, there's another situation that exists where you have, how about no point of intersection? So no point of intersection, I was going to write interesting, intersection. So no point of intersection, so no POI. So the only way that two lines will never ever touch each other is if they're running alongside each other. So whatever the slant is, repeat the slant. So in this particular case, we have two lines running alongside each other like railroad tracks. So we would say that there's no point of intersection. These lines will never ever touch each other, ever. They're always going to stay the same distance apart. So that means lines never intersect. How are their slopes related? So lines are parallel. If you remember that from grade 9. So lines are parallel. They have to be parallel in order for this to happen. So the slope of one line must equal the slope of the other line. They must be the exact same slope. So same slope. Now the y-intercept, though, you notice that how I drew them? This y-intercept is up here, this y-intercept is down there. The y-intercept must be different. Must be different. So because the y-intercepts must be different, these lines will never touch. If they happen to be the same, then that becomes a point of intersection. So we know that the y-intercepts must be different. So again, this is the clues you look for. These are the clues you look for in y equals mx plus b. You look at the slope. If the slope matches and the y-intercept is different, then you know that you have this situation. Now, when it comes to standard form, The coefficient of this line and the coefficient of this line for x's and y's will match. So the coefficients match. So the coefficients for x and y match when in standard form. But I have to point out here, not the constant. The constant doesn't match when in standard form because they're still two different equations. All right, so now the last case. So we have touching once and we have never touching. The last case is going to be always touching. So what does it look like when we have two lines that are always, I don't know if this is dark enough, two lines that have infinite number of points of intersection. Infinite number of solutions. So we would say that the only way that can happen is if one line and the second line are always touching, which means they are on top of each other. So lines are on top of each other. This is called coincident. So they're the same line, technically. They're in the same location. So this is a point of intersection, this is a point of intersection, this one, this one, this one. Infinite number of points of intersection. They're all points of intersection. So how do you know you have this situation? Well, obviously, if it's the same line that you're going to be end up graphing twice, they must have the same slope and they must have the same y-intercept. So if you see the same thing in y equals mx plus b format, so the m's match and the b's match, then you know that you have coincident lines. Now, when they're in standard form, the coefficients must also match, because again, it's the same equation written twice. So the coefficients for x and y match, and the constant matches. In standard form. Okay, so that was for standard form. The x, y, and the constant matches, whereas before the constant was the one that didn't match. Here the constant also has to match. Basically, one equation is a multiple of the other. So you have to look at, does one equation reduce down to what the other equation already looks like? So basically, one equation is a multiple of the other. So we're going to go through some examples to see which one of these three situations, right, 1 POI, 0 points of intersection, or infinite number of points of intersection, looking for these clues based on how the information is given to us. So in the first case, notice, because it says determine the number of points of intersection. So notice that you're given y equals mx plus b, y equals mx plus b. So in this case, we're just going to compare slopes and y-intercepts with each other. What we're interested in to know are, do the slopes match, do the y-intercepts match? So here we have different slopes, same y-intercept. So different slopes, so they're not parallel, they're not coincident, but we happen to have the same y-intercept. So this means that because they have different slopes, they touch once. So 1 POI. It happens to be the y-intercept. Doesn't always have to be the y-intercept, but it happens to be the y-intercept because they both go to -1 on the y-axis. So the y-intercept happens to be where these two lines touch. So this is the first case, the common case, right, where two lines have one POI. Second scenario, again, they're in y equals mx plus b. So again, we compare m and b. The slopes match, the y-intercepts don't. So we have same slope. So right away, as soon as I see same slope, I know they're at least parallel. Y-intercepts are different. So they're not the same line. So that means if they have the same slope but different y-intercepts, they're parallel but distinct. Distinct means separate. So they both run the same way, but they're not on top of each other. That's coincident. This is parallel but separate because of the y-intercept makes them separate. So we know this is now parallel. Oops, why did I make that a T? Parallel and distinct. Which means parallel and distinct means that they will never touch, right? Because they're separate. So this means no solution, no POI. Okay, because they're two different lines that never touch each other. The next case is different because it's not given to us in y equals mx plus b. So right here we have standard form, and the second equation is standard form. So when lines are given to you in standard form, you have two options. You can convert them both into y equals mx plus b, which is a pain in the butt, especially when you have coefficients that aren't nice. Or you can check for the coefficients to see if they match or if one is just a multiple of the other. It's your choice. So if I was to convert to y equals mx plus b, just to show you, I would take this first equation. I would kick the 2x and the minus 7 to the other side of the equal sign. So leaving me with 3y equals negative 2x plus 7. And then I would divide everything by 3. And you're left with y equals negative 2/3 x plus 7 over 3. Okay, so that's our first line. Then we would do that for the second line. Again, you can keep the negative 6y on this side, or I'm going to kick out the 6y actually to the other side to get positive 6y. So the negative 4x will stay, the positive 14 will stay, giving me 6y on that side. So now he's positive. Divide by 6, divide by 6, divide by 6. And of course, don't leave a 4 on top of a 6. Reduce. That becomes negative 2/3. Don't leave a 14 on top of a 6. Reduce by 2. So that's 7 over 3. And 6 divided by 6 is y. So now that they're both in y equals mx plus b, you definitely see that there are definitely things that match. Negative 2/3 x, negative 2/3 x, that matches. Positive 7 over 3, positive 7 over 3, that matches. So what you see here, which wasn't obvious before, is that they have the same slope, same y-intercept. So in comparing slope and y-intercept, what we see is same slope, same y-intercept, which means coincident. They are the same line. And if you're coincident, what does that mean? Infinite. All points are a point of intersection. So infinite number of solutions or points of intersection. Infinite number of solutions. So that made it a little clearer to see. Now, could we have noticed that without actually converting the equations? The answer is yes. So do you see that 2 times negative 2 would have given me negative 4? If I times so big fat, or we could have just multiplied 1 by negative 2 just to see if they match. Or you could divide the second equation by negative 2, same thing. So if I times the first equation by -2, I get -4x, -6y, +14 equals 0. Compare to equation 2. -4x matches, -6y matches, +14, the constant matches. All coefficients, why I put an N in there? Coefficients and constant match, which therefore again means that they are the same line. It's the same equation. The 2 became a -4, which matches. The 3 became a -6, which matches. And the -7 became a +14, which matches. So whether we reduce the second equation down or we multiplied up the first equation, they ended up becoming and looking the exact same. So let's try that method over here. I'm not going to convert to y equals mx plus b. I'm just going to look. So just by looking, what do we see? Okay, 5 matches 5. Good. +2, -2. Oh, we got different signs, but the -1 matches the -1, so those match. So they're not quite the same. They're not exactly the same, not like over here. So they are not coincident. The sign is going to be off. So they're definitely not the same line. They're not going to have the exact same slope. So in this case, we're back to one point of intersection. So if you wanted to again verify, so these don't match. Okay, so I don't want you to think that the signs don't matter. The signs have to match as well. So if I did convert to y equals mx plus b, we get 2y equals -5x, +1, divide by 2, divide by 2, divide by 2, -5 over 2x plus 1/2. Do the same for the second guy. 5x minus 1 equals 2y, divide by 2, divide by 2, divide by 2. Y equals 5 over 2x minus 1/2. Notice the signs are different. So this has a negative slope, this has a positive slope. Everything was flip-flopped because the coefficient in front of the y was different. Here we were dividing by +2. So what that means is different slopes, different y-intercepts mean different lines. So what that means is one point of intersection. These are just random lines. So this is your common situation where you have just one POI, even though the equations almost look exactly the same, that one little change made certain that they would touch just once. All right, see you again.